Mean time and time between collisions. Consider an ion of charge Q and mass m immersed in a gas and subject to an electric field epsilon in the z direction. For purposes of simplicity, assume the following model. An ion travels in the z direction, starting always from rest after each collision, and moving with an acceleration a is equal to q epsilon over m for a fixed time t sub c. It is then brought to rest by the next collision, and the whole process starts over again. A plot of the velocity v of an ion as a function of time would then have the appearance shown in figure. So the ion is brought to rest, and then it accelerates in the z direction, brought to rest, accelerates in the z direction, and brought to rest. So the time between collisions is Tc. Part A. Consider an ensemble of such ions at an arbitrary instant of time, so at time t. What is the mean time tau which elapses before an ion suffers its next collision? Express your answer in terms of the time tc between successive collisions. So the mean free time tau which elapses before an ion suffers its next collision starting at an arbitrary instant in time. Okay, so let's define probability p of t dt, probability density function p of t dt, be the probability of having a collision in the time interval t to t plus dt. Okay, so in this time interval, what is the probability of having a collision? It's p of t dt. Now, what is this probability? If you think about this, this probability is equal to 1 if the time interval is equal to the collision time, tc. So this is actually dt divided by tc. It's proportional to the amount of period between t and t plus dt, so that's basically proportional to dt. The longer I wait, the higher the chances that there will be a collision. And what is the time I should wait to make sure that I will encounter a collision? Starting at any point in time, if I wait for a time interval tc, it's certainly true that even if I start here and wait for a time tc, there will be one collision. So this probability is dt over tc. So we note that if the time between t and t plus dt is delta t, and that delta t is equal to the collision time t sub c, the probability of having a collision will be 1. So the probability is then going to be 1. Okay. Now, what is the mean time tau which elapses before an ion suffers its next collision? The mean time that elapses tau before it suffers its next collision, which is t bar, is the integral from 0 to tc, the collision time, t probability of t dt. So this is the integral from 0 to tc, t dt over tc, because dt over tc is our probability. And that's going to be equal to 1 over tc. The integral of t dt will give me t squared over 2. so that is t squared over 2, evaluated between time t is equal to 0 and the collision time tc, and this will give me tc squared divided by 2tc, and that mean time that elapses before the next collision occurs will be equal to tc divided by 2. And that basically makes sense because we have a linear dependence on time. So for example, if I am here, then I have to wait a time tc. If I am here, then I have to wait for a time much less than tc. So if I'm right here, then I don't have to wait at all. I wait for 0 seconds. So what is the mean value between this waiting for tc and waiting for no time? It's going to be tc over 2 because of this linear dependence on time. So that is basically intuitive. So the time I have to wait, the mean time I have to wait, starting at an arbitrary instant of time t, before the ion suffers its next collision, is the collision time tc divided by 2. Part B, what is the mean time which has elapsed since an ion suffered its preceding collision? Express your answer in terms of tc. Now we are at an arbitrary time t. We want to know how much time has elapsed before the preceding collision. But we have time reversal symmetry here. So because of time reversal symmetry, we can argue that the answer should be the same. The answer is the same. The mean time I have to, the mean time that has passed after the preceding collision until I reach time t is tc over 2. Okay, so first I looked at how much time I have to wait before the ion suffers its next collision. Then I considered the time that has elapsed after the preceding collision, and they are both equal to tc over 2 due to time reversal symmetry. Part C, what is the maximum velocity ever attained by an ion? What is its mean velocity v bar? Express your answer in terms of collision time tc. Express it also in terms of the mean time tau of part A. Now, the ion experiences an acceleration in a time interval tc. You can see that the velocity is increasing in time. Velocity is a function of time. So it attains its maximum velocity starting at t is equal to 0 at time tc. So the acceleration is the basically v maximum minus v minimum divided by delta t, because it's a constant acceleration motion. This is going to be v max divided by the collision time tc. So we can see that the maximum speed it will have is the acceleration a multiplied by the collision time tc. Now, what is the mean speed it has? V bar. V bar is integral from 0 to tc, acceleration times t, because I know that v of t is at for t between 0 and tc here. So this is at p of t dt, and that's going to be the integral from 0 to tc at dt divided by tc. So if I do this formally, and this is going to give me for the mean speed of the particle for the ion v bar the integral t dt gives me t squared over 2. So I have a divided by acceleration a divided by the collision time tc multiplied by t squared over 2, which is tc squared over 2 when evaluated between 0 and tc. So these two will cancel, and I will find the mean speed to be atc over 2. Not surprisingly, it is half of the maximum value. Now, because tc over 2 is tau, I will see that the mean speed is acceleration times the mean time, which is also not surprising. So it's expressed in terms of collision time, and it's expressed in terms of the mean time that elapses before the next collision, or that has elapsed after the preceding collision. And this acceleration A is basically the force, electrical force, Q epsilon divided by M. That is the only force in action. Now, part D. What is the distance s traversed by an ion in a time tc, collision time, starting from rest? If we define the mean velocity of the ion by v bar is equal to s divided by tc, what is the value of v bar thus calculated? Express your result in terms of tc, express it also in terms of tau, and compare with part C. The distance traversed by the ion in a time interval tc, because its velocity is a times t between 0 and tc, this is integral 0 to tc at dt, which is 1 over 2 at squared, constant acceleration motion, evaluated between 0 and tc. This will give me, for the distance traversed, 1 over 2 atc squared. So that is the distance traversed. And now v bar is defined as the distance traversed divided by the collision time tc. Then it's going to be equal to 1/2 atc squared divided by tc, which is 1/2 atc. So it is atc divided by 2, which is equal to a times tau. Okay, so if we compare this result to the result of part C, the result of part C was basically v bar is equal to atc over 2, or a tau. It's basically exactly the same thing. So this is same result as in part C. Okay, so we're looking at an ion, a model for an ion that is traveling in the z direction under an applied electric field epsilon. The ion has mass m and charge q. It's immersed in a gas. And for simplicity, we assume that the ion travels in the z direction, and it is under the influence of this force q epsilon in between collisions, so that it has a constant acceleration motion q epsilon over m acceleration for a fixed time tc, and in every collision it is brought to rest and the whole process starts again. So I reset the timer here. Between 0 and tc it's accelerating, it reaches its maximum speed, and then it stops, and then the whole process starts again. Now, what is the mean time that elapses before an ion suffers its next collision starting at an arbitrary instant in time? At t is equal to 0, I have to wait for a time tc. At t is equal to tc over 2, I have to wait for a time tc over 2. At t is equal to 3 over 4 tc, I have to wait for 1 over 4 tc to have a collision. So if I consider an arbitrary time t, what is the probability of having a collision in the time interval t to t plus dt? It depends on what dt is. If the dt is equal to the collision time, then we are guaranteed to have a collision, because if I start at tc over 2, I wait for a time interval tc, the collision has occurred. in between these 2 points in time. So the probability is going to be equal to 1. Therefore, using this probability density function, I find the mean free time to be integral 0 to tc t p of t dt. That is using the definition of the mean value. We find that this is t dt divided by tc, integral 0 to tc, and this probability is normalized. So I can see that this is 1 over tc times tc squared over 2, which is tc over 2. And you can see that also from this linear relationship, if you wait for, on average, if you wait for a time tc over 2, you will see a collision. Obviously, if you start here, that's not going to be the case. You have to wait for tc. But on average, we have to wait for a time interval, tc over 2, when you pick time values in this range. Now, because of time reversal symmetry, the time that has elapsed after the preceding collision is also equal to tc over 2. The maximum speed it attains at time t is equal to tc starting from 0 is basically telling me that the constant acceleration is Vmax over Tc, which tells me that Vmax is A times Tc, and the mean speed is, using this probability density function, the speed at time t, At, where time is between 0 and Tc, P of t dt, and you can see that this gives me Atc over 2, or A tau, or it's Vmax over 2. That is the mean speed, and that is also obvious here. The mean speed it has between 0 and Vmax is Vmax over 2. Now the distance traveled between 0 and Tc is V of t dt, which is At dt integral. That gives us 1/2 Atc squared. This is constant acceleration motion, and the mean speed is s divided by Tc. That is the we define the mean velocity as s divided by tc, the distance traveled, divided by the collision time. And this also gives us the same answer. The mean speed is atc over 2, or a times tau.